The Jesus V. Del Rosario Foundation Incorporated is a foundation that has been providing valuable assistance to the less privileged but deserving sectors of our society. For almost 2 decades now, JVR Foundation has fulfilled the role of a partner in the effort to improve the lives of countless individuals. It is well known as an able provider and implementer of educational scholarships, professional development programs, and various charitable activities. Its founder, Mr. Jesus V. Del Rosario, a distinguished entrepreneur who pioneered numerous successful business ventures in the country, heads the foundation. Under his leadership, JVR Foundation has blazed the trail in charity and social work, particularly in the areas of training and educational development. Having realized the importance of uplifting the levels of teaching proficiency in our country, the Foundation has chosen to break new grounds by pioneering the production of seriously needed teaching materials. Advocating for a more responsive and relevant science teaching, JVR Foundation Chairman Jaime C. Del Rosario has vigorously pursued the making of this training video, the Science Teacher Training Video Series number 1. It will function as the teacher's readily available guide in teaching of science concepts in the classroom. The production of the video series was designed to address the difficulties encountered by the teacher in conducting interactive science activities. This teacher training video is about physics. Intro to Physics. Physics is the science devoted to the study of energy and its effect on matter. There are 2 methods of studying physics: theoretical and experimental. Theoretical physics is the theory building. Here, laws and theories are developed by physicists using logic as their tool. Their laboratory is their brain. The most popular theoretical physicists are Hawking, Einstein, and Newton. Classical or experimental physics deals with experiments. The main objective is to prove or disprove what theoretical physicists have discovered. Learning physics through the utilization of energy. Energy is everywhere: light, heat, and sound. When we talk of energy, we must talk about the whole universe. Remember your lessons in general science? Here are some basic principles we learned then. First, we were told that the whole universe is said to be made up of matter. Second, we also learned that energy and matter are equal. Remember the formula E equals mc squared? Third, energy can only happen if there is matter. Fourth, whenever matter is changed in any manner, it is transformed to energy. Hence, any loss in matter becomes energy. Since the whole universe is matter, then when one talks about energy, necessarily we have to deal with at least one component of the universe. Through time, energy has been with us. Energy affects our economic growth and our society in general. Light. In Genesis, God said, "Let there be light." What is light? Light makes it possible for us to see. Light comes to our eyes, and this makes seeing possible. Without light, we would have no food to eat or air to breathe. Plants use the light from the sun to grow and to make food. Light from the sun also heats the earth. Without the sun's light, the earth would soon become so cold that nothing could live on it. Sources of light. Many of the things we see, such as the sun, a flashlight, and room lights, are sources of light. We see all other things because light from a source bounces off them and travels to us. Classification. Light sources can be classified as natural or artificial. Natural light comes from sources that we do not control. Such sources include the sun and the stars. Artificial light comes from sources that we control. These sources include candles and flashlights. Objects that emit light by themselves are called luminous bodies. They are active sources of light. Temperature. Sources of light vary in temperature. We will show you two experiments to demonstrate what we mean. Activity number 1. The sensory measurement of the temperature. In the following experiments, we will be needing a candle, a match, optical board, power supply, 2 connecting wires, small lamp socket, miniature incandescent bulb, big lamp socket connected to 220-volt line, fluorescent lamp. This is our setup. Experiment 1. Lighting a candle. In our first activity, simply place a candle on a board and light it with a match. What happens? Observe the light it gives off. Experiment number 2. Lighting an incandescent lamp. Let's move to the next experiment. Procedure. Screw in the bulb into the lamp socket. Plug the power supply to 220 power outlet. Check if the LED lights. Using 2 connecting wires, connect it to the power supply. Get one of the connecting wires and clip it to terminal A of the power supply. Get the second connecting wire and clip it to terminal B of the power supply. Now you see an incandescent bulb light up. Incandescent light is a light produced by a hot filament when its temperature is about 2,200 degrees centigrade. This was first invented by Thomas Alva Edison in 1878. This type of lamp has been very popular until the early 1950s. You still get to see them in some of your houses which use the yellow bulbs. In the Philippines, people refer to this as bombilya. Experiment number 3. Lighting a fluorescent lamp. In our third experiment, we will need the following. A big lamp socket connected to 220-volt line. Fluorescent lamp. Procedure. Plug in the lamp into a 220-volt line. To make this experiment more dramatic, let's turn off the room light. White light. Fluorescent lamp emits white light. In the 1920s, Edmund Germer invented the fluorescent lamp, which has become a popular alternative to the Edison lamp. It has been said, though, that our own Agapito Flores invented this lamp earlier on, and many Filipinos acknowledge him as the inventor of the fluorescent lamp. Activity number 2. Measuring the temperature through the color of the bulb filament. Using the incandescent lamp setup, let's demonstrate this method of measuring temperature. Procedure. In order to measure the temperature of the lamp using the color of the bulb filament, we need to add 2 connecting wires and the wiper-controlled wire-wound rheostat. This type of the rheostat uses a long resistance wire coiled around an insulator which controls the flow of current from the source into the wire. The ability to control the flow of the current through the rheostat allows us to observe the gradation of color of the bulb filament as we increase or decrease the electric current that flows through the wire. Please take note that there are 3 terminal screws, 2 of which are in contact with each other through the resistance wire. Third terminal is attached to the wiper contact. Now, let's attach 1 connecting wire to 1 terminal screw of the rheostat and the other one to the terminal screw of the wiper contact. You have now put together a closed circuit connection in lighting your lamp. Place a projection screen or a white screen using laundry clips as stand and place it on one end. In between the projection screen and the source of light, place a double convex lens. Now, let's turn off the room lights. When the lamp's filament starts to become red hot, focus the image by shifting the lens until sharp picture of the filaments appear on screen. Slowly move the wiper arm of the rheostat, gradually increasing the current. Observe the difference in the filament color. Since we cannot measure with a thermometer the temperature of the filaments at different currents, the temperature is approximated by the filament color. Low current is indicated by the red color filament. Medium current is indicated by the bright yellow color filament. Maximum current is indicated by the white color filament. Conclusion: the brighter the lamp, the hotter it is. The brightest and the hottest source of light is the sun. The temperature of the surface of the sun has been determined at 5,600 degrees centigrade. We have also learned in this portion that light, as you have seen, can be produced through several means: by combustion, by incandescence, by electrical discharge as in lightning, by electric arc as in electric welding, by carbon arc as used in old movie projectors, by fluorescence, by phosphorescence, by bioluminescence. Activity number 3. Light has the same amount of reflection on all sides of the source of light. In this activity, materials we will need are the following: white screen with 2 clothespins to serve as stands, a bulb in a lamp socket connected to 2 connecting wires, a 5-volt DC power supply. Procedure: connect the 2 ends of the connecting wires to terminal A and terminal B of your power supply to give you 6 volts. Let us move the screen farther away from the lamp. Notice that the reflection on the white screen gets dimmer as the screen moves away from the light source. Now, let us revolve the white screen around the lighted lamp, making sure the distance of the screen remains the same equidistance from the light source. Is there a difference in the reflection of the light? You are right. Wherever you move the screen, the reflection remains the same. Conclusion: the white screen, although is not the source of light, has become an active source of light through the principle of reflection. The farther the white screen from the light, the dimmer the light that is reflected. The farther an object from the source, the less light it gets. The light reflected on the white screen is equal when placed in an equal distance from the lamp. Light is propagated equally in all directions. Activity number 4. Light travels in a straight line. Experiment number 1. Using a comb. Materials: power supply, 2 connecting wires, bulb in a lamp socket, lamp house, comb supported upright by 2 clothespins, white screen attached to 2 clothespins to keep it vertical, optical board. Procedure: cap the bulb with the lamp house. Connect the connecting wires to terminals A and terminal B of the power supply. See what happens. What do you observe? We now have created a tiny spotlight. We will center this spotlight on the teeth of the comb. Now, let's turn off the room lights. What do you observe on the optical board and on the white screen? On the optical board, you can see a spread of non-coherent light. Rays of light in V formation is observed. Now let's do some magic. Play with the comb, calibrating the distance from the lamp house. The closer the comb from the light source, the fewer and thicker light rays can be observed. The farther the comb to the light source, the more light rays are generated. Also, the thinner the light rays have become. Conclusion. What we have created are shadows. Unlike Peter Pan, who tends to lose his shadow, our experiment shows that at no point in time when light strikes an object that shadows will not be created. Whenever there is light, there is shadow. Light always moves on a straight line, and when it hits an obstacle, a shadow is created. Light cannot go around an obstacle. It always hits the object on a straight line. Light also behaves differently depending on how close one is to the source. This has been demonstrated by our comb experiment. As we have seen, the closer the comb from the light source, the fewer and thicker light rays can be observed. The farther the comb to the light source, the more light rays are generated. Also, the thinner the light rays have become. Experiment number 2. Using pencil. The next experiment reinforces what we have just seen. Materials. Let's use a pencil this time, using the previous setup but without the comb. Procedure. Between a white screen at one end and a lamp house at the other end, hold the pencil in the center of these two at a vertical angle on the optical board. Making sure the room is very dark, switch on the two lamp houses. Example, flashlights. What do you observe? Now, let us just use one source of light. Do you see any difference? You are right. There is just one shadow. Depending on the light source, you can observe multiple shadows. Let us see what happens if we have several sources of light. Using two sources of light, two shadows appear. Add another one, and what have we got? 3 shadows. Note, if no multiple sources of light is available, you can use flashlights in the classroom. Conclusion. Creation of shadow is a proof that light travels in a straight line. As you have seen, multiple sources of light generate multiple shadows. The number of shadows is a function of the number of sources of light. Our third activity, still on shadows, will show us another very important feature in the discussion of lights and shadows. Experiment number 3. Using pentel pen. Materials. Old setup. Additional bulb and lamp house. Additional 2 connecting wires. 1 pentel pen. Procedure. Using the old setup, connect the additional lamp house to the power supply. Place the pentel pen on its upright position between the lamp houses and the white screen. Turn off the room lights. As we have seen earlier, with 2 sources of light, we generate 2 separate shadows. Move the 2 lamp houses towards each other until they meet. You can also show this by using a mirror instead of a pentel pen. Conclusion. At the point where the 2 shadows meet or cross each other, it is called the umbra. In Latin, means shadow. While the shadow created by only one of the 2 lamps is called penumbra, in Latin, it means almost shadow. Activity number 5. Seeing is a function of how light travels through a pinhole. How do we see? Seeing is actually capturing images, and light plays a very important role. When we see an object, it reflects light, and that whole reflection of light must enter into our eyes in order for us to see the whole object. But we only have a pair of very small holes, which is our lenses that must capture this whole reflected image. Let us discover the mystery of seeing. First thing we have to remember is that every single point of an object emits multiple light rays traveling at straight lines that go at different directions. As we have learned in our earlier experiments, when light strikes opaque objects, they are either absorbed or reflected. Hence, the light rays and their corresponding images do not cross over to the other side of the opaque objects. However, when there is a pinhole on the surface of an opaque object, there is a place where the light rays can go through. But not all rays can do this. Only the light rays that are rightly angled and can go through the hole are the only ones that can cross over to the other side. When these light rays manage to go through the pinhole, they carry with them the corresponding parts of the image they reflect. Necessarily so, as shown in the picture, what gets across through the hole to the other side of the obstacle is the inverted image. How do we demonstrate it? Materials: optical board, a candle, an improvised pinhole camera, a magnifying glass. Procedure: mount a lamp on the optical board as shown with a screen at the extreme end of the board. In between, place a white board with a small hole at the middle. Turn off the light. What do you see? How does that happen? Why is the image inverted? Conclusion: how do you see? Seeing is capturing images, and light plays a very important role. In reality, this is how we see. Images first pass through the opening of the front of our eye, the pupil, to the lens, which inverts the image and projects it onto the retina. The retina processes the image and delivers it through our optic nerve, which, in turn, transmit nerve impulses to the brain. The brain tells us what we see. Hence, in truth and in fact, it is actually our brain that sees. Activity number 6. Ability of light to pass through objects. Different types of lights behave differently when they pass through different types of objects. Let us do some experiments to show what we mean by this. Experiment number 1. Using diffused light. Materials: power supply, 2 connecting wires connected to a lamp socket with a bulb, white screen with 2 clothespins. Optical board, a piece of clear glass, a piece of frosted glass, a piece of cardboard. Procedure: clip the connecting wires to terminals A and B. To better appreciate this experience, let us turn off the lights. Place the clear glass between the bulb and the white screen. Did the light pass through the transparent glass? Yes, it did. Now, let us try to use a frosted glass. Did the light behave the same way? No. The image on the white screen is not as clear as when it passes through a clear glass. Now this time, let's use a piece of cardboard. What did you notice? No light rays passed through the cardboard. Don't forget what you have just observed. Meantime, let's move to the next activity, and let us change the source of light to something more focused. Experiment number 2. Using focused light. Materials: use the same setup but change the source of light. Laser light mounted on a clothespin. Procedure: put on your laser light. As you can see, the light produced is a much more directed light. Let us turn off the room lights. Place the clear glass in between the laser light and the white screen. Did the light pass through the transparent glass? Yes, it did too. The laser light easily passed through the clear glass. Now, let us try to use a frosted glass. Did the light behave the same way as the first demonstration? No. What came out is a beautiful image which demonstrated that some light rays were refracted. Now this time, let's use a piece of cardboard. What did you notice? No light rays pass through the cardboard, even if the laser light is a focused light. Conclusion. In both experiments, the following principles have been demonstrated. Light passes through transparent material very easily. Translucent material diffuses light. Some light rays pass through or get transmitted. Others are refracted and others are reflected. Opaque materials do not allow light rays to pass through it. If the opaque surface is white, it reflects the light rays back to the source. If the opaque surface is black, it absorbs the light rays. Activity number 7. Angle of incidence is equal to angle of reflection. Lights also behave in some specific ways. Another principle of light that remains inviolate up till this time is that the angle of incidence or entry will be equal to the angle of reflection or exit. How do we demonstrate this? We prepared 2 activities to show this. Let us start with the first one. Experiment number 1. Normal position of protractor. Materials: laser pointer, optical board, protractor, mirror. Procedure. On the optical board setup, the protractor with a plane mirror is aligned on top of it and is facing you. Then beam the laser pointer on the other side to the mirror at exactly 90 degrees normal to the protractor. Observe the reading on the protractor where the laser light reflects. Notice the laser beam goes back to you. Conclusion. A beam that is directed at 90 degrees of the protractor will be reflected exactly back to the source. Experiment number 2. Normal position of protractor. Let us try directing the laser beam through different angles to the mirror. If point of entry is at 15 degrees, then point of exit is at a 15-degree angle at the opposite side. If point of entry is at 30 degrees, then point of exit is at a 30-degree angle at the opposite side. If point of entry is at 45 degrees, then point of exit is at a 45-degree angle at the opposite side. If point of entry is at 60 degrees, then the point of exit is at a 60-degree angle at the opposite side. The angle formed by the incoming light ray with the normal is called the angle of incidence. The angle formed by the outgoing light ray with the normal is called the angle of reflection. When we changed angles of entry of light in the first activity, what we have been doing so far is moved our angles of incidence, the point of entry of light. We observed that the angles of incidence are equal to the angles of reflection, the point of exit of light. All this time, our reflector, the mirror, remained to be in the same position. Let us see if these observations will remain the same if we now change the angle of the mirror. Experiment number 3. Protractor at different positions. Now, supposing we change the angle of the reflecting source, which is the mirror. Do you think we will get the same equal relationship between angles of incidence and reflection? Procedure. With the same setup we have earlier, let us rotate the mirror at 75 degrees without moving the protractor on which it stands. By doing this, we also moved our true zero, or the normal, by 15 degrees. 90 degrees minus 75 degrees equals 15 degrees. When we beam the light, where do you think will the angle of reflection be? You are right. The light came out at angle 30 degree R, because 15 degrees multiplied by 2 gives you 30 degrees. Let us try another one. Let us move the mirror to 60 degree L. This means our true 0 degree is now 90 degrees minus 60 degrees, which equals 30 degrees. We multiply this by 2, and truly that is where our angle of reflection is. This time, the light came out at angle 60 degree R. Do you think your angle of incidence is equal to the angle of reflection? Considering that your beam of light entered at 0 degree normal position? The answer is still yes. Because what you did was just to turn the whole mirror such that the true 0 degree technically moved along with the mirror, despite the fact that you beamed your light at the visual 0. Conclusion: we have now strongly proven that the angle of incidence is equal to the angle of reflection. Activity number 8. Principle. Knowing that light rays travel in a straight line, we can manipulate them. Because we know light rays travel in a straight line, we can actually play around with them and work them to our advantage. What we have next is a series of activities which allow us to practically paint or do some graphical designs using light rays. Let us prepare our materials for this series. Materials: power supply, lamp with the lamp house attached to the connecting wires, concave lens and convex lens, comb using laundry clips as a stand. Procedure: make a circuit connection at one end of the board. With this setup, let us turn off the light once again. Experiment number 1. Using a comb. Let us first create parallel lines. See this comb? This will do magic. Place the comb in front of the lamp house. What do you see? We see rays of light spreading out in front of the comb. Comb in front of a source of light produces light rays. Experiment number 2, using a concave lens. What else can we do with our parallel lines? This time, let us see what magic a concave lens can do. Let us now try to catch the parallel lines created by the comb with our concave lens. Oh boy, we have actually created a nice spray of light rays. Conclusion: concave lens widens the light rays in the spray. Experiment number 3, using a convex lens. Hey, isn't that exciting? This is getting more and more interesting. I have here another piece of wonder. What trick would a convex lens do to our spray of light? Now, let us try to catch the spray of light rays using a convex lens. What happens? The light rays have been caught by the convex lens and bundles them into one beam of light. Conclusion: convex lens closes rays of light into a focus. Experiment number 4, using a bent stainless strip. Did you see that? If in literature we have the taming of the shrew, in optics we have the taming of the lights. But that is not the end of magic. We have more tricks in our sleeves. We now have a bent stainless strip, angled as a convex mirror. Let us now place this bent stainless strip angled as a convex mirror in front of our bundle of light rays. Hey, look at those light rays turning back into a spray. What do we do if we turn the stainless strip into a concave mirror? Wait, the rays caught originally by the convex mirror when caught by a concave mirror, have folded back and focused into a single point. Conclusion. When light rays hit a bent stainless strip, which serves as a convex strip, the light rays form into a spray of light. When a concave mirror catches this spray of light, the lights fold back and are pulled together, meeting into a single point. Experiment number 5. Switching concave and convex lenses. Switch the positions of the concave and convex lenses. Observe what happens. Where did the path go now? What caused it to follow that path? Conclusion. Concave and convex lenses create specific paths of light. Concave lens widens light rays while convex lens gathers the rays of light into one single point. Experiment number 6. Using 2 convex lenses. Let's try using 2 convex lenses this time. What did you observe with the light rays? What made it follow that path? Conclusion. Once again, we saw that the convex lens causes the light rays to converge at a point called the focus. Experiment number 7. Using a triangle prism. Isn't that great? Well, I have another exciting experiment here. See this? This is a prism. What trick would this right-angle prism give us? Now, what if we replace the stainless strip with a right-angle prism? Make sure that the rays enter the prism from the center. Where did the rays go? Why did it differ from the previous experiment? Why do you think so? Conclusion. A right-angle prism creates bending light rays whenever light passes through it. Now, let us rearrange the triangle so that the rays of light will enter from a different side. This time, make sure that the rays enter the prism from the side with the longest leg. Where did the light rays go? Conclusion. A right-angle prism reflects light as if it were a mirror. Experiment number 8. Using a rectangular prism. This time, let us try replacing our light source with a laser beam. Using a rectangular prism, let the laser beam pass through it at 90 degrees. What did you observe? Experiment number 9. Using a rectangular prism at an angle. Using the same setup, shift the laser beam so that it enters the prism at an angle. What did you observe? Did the laser beam continue a straight line as before? Conclusion. A rectangular prism allows the laser beam pass through unaffected when it enters at 90 degrees. But when a light ray passes through the prism at an angle, it is bent. This is the property of light that allows both animals and humans to see objects. It is only when light reaches our eyes as it bounces from an object that we actually see the object. Activity number 9. Principle. The intensity of light or light's luminance can be measured using certain devices. A photometer measures the intensity of light. One example of this is the Jolly's photometer, a cylinder of paraffin wax with a metal strip at the middle, separating the semicircular sections exposed to light sources. This photometer is now obsolete, but was used to determine the luminance of a light source by comparing it with a known luminance. The formula is: the modern equivalent is the electric photometer, which consists of a small solar cell and a sensitive galvanometer. Let us see how a photometer works. Materials: 2 lamp houses, optical board, Jolly's improvised photometer. Procedure: set up the apparatuses as illustrated. 2 lamp houses are placed on opposite ends of the optical board. Then, the Jolly's photometer is placed in between the light sources. Slowly move the rheostat from one side to the other. Observe the luminance of the light from the two sections of the photometer. What do you observe on the photometer as we move the rheostat? Conclusion. By using a photometer, one is able to observe more closely the increase of the intensity of light and allows one to study the behavior of light. Concluding statement. The study of optics in the high school is often inadequate because of lack of optical apparatuses to show or demonstrate the different optical concepts. What you have seen so far in this VCD are just a few illustrative ways of engaging the students to learn the basic concepts in light production, propagation, reflection, refraction, absorption, and transmission. You have been given the tools and the examples of how to create more magical experiments that would delight the students. Allow the magic to do its work and make the study of physics an enjoyable experience.